Morning. Welcome to the session on mapping of address and port using translation. I'm Jordan Gottlieb, and I'm a member of the Network Engineering and Architecture Group at Charter Communications. Quick show of hands, how many of you are familiar with MAP-T? All right, not too bad. Well, this is going to be an introduction to MAP-T, as well as some information regarding the rationale for advancing this technology, as well as the state of MAP-T at Charter Communications. So what is MAP-T? It's one of two transport modes of the parent technology MAP, which aims to transport IPv4 over an IPv6 domain. Now, MAP-E uses encapsulation. It uses the same encapsulation as DS-Lite, where an IPv4 packet is prepended with an IPv6 header and transported across the network in that way. MAP-T uses IPv4, IPv6 stateless translation, so you've got header translation as opposed to encapsulation with MAP-T. The addresses, the IPv4 addresses, are embedded within the corresponding IPv6 addresses in order to create a tunnel or softwire. Now, our primary application for MAP-T, though it doesn't have to be implemented in this way, is to support N-to-1 IPv4 address sharing. This is similar to the competing technologies, carrier-grade NAT, large-scale NAT, but it differs in the sense that the service provider gateway component is stateless. It's actually mostly stateless, and I'll cover that later. It also differs from the perspective that the subscriber router actually receives the public IP address, the shared public IP address, logically speaking. And because this is a shared IPv4 address, it also receives a port set identifier, which is an index into a set of ports, a unique set of ports that it's allowed to use. So we have a pretty varied audience here at NANOG. We've got content providers, service providers, other verticals. Why would MAP-T and actually other address sharing techniques be of interest? Well, we're all dealing with IPv4 address exhaustion, and it's obviously causing us some significant issues. And eventually, shared IPv4 is going to be a more significant consideration, especially for the content providers. Why? Well, if you're doing licensing based on IP address, this is something you're going to have to consider in a shared IPv4 addressing world. If you're doing reputation by IPv4 address, that's going to be an issue for you as well. Geolocation, possibly. This is going to depend on implementation. As I mentioned before, subscribers are going to be assigned a specific set of unique ports, so you don't have the scale of 16 bits worth of multiplexing. So that is going to be reduced, and that is going to be a consideration as well. If you're implementing any peer-to-peer applications in a shared IPv4 world, triangular routing may or not impact performance and latency. There are going to be some implication. The posture that you see today with UPnP IGD and static port forwarding, that's going to be different as well. These are things you really are going to want to consider. UDP hole punching techniques shouldn't be impacted because most of the transition technologies do a pretty reasonable job of endpoint independent mapping and other mechanisms for NAT transparency. That being said, I think having a serious IPv6 strategy behooves us all because ultimately we're all in the business of servicing our customers and we want to do it well, and long term that's going to mean IPv6. Those of you who work for service providers, especially those who service broadband residential subscribers, I'm very interested in your interest for potential of adoption and helping me move this technology forward and making it more of a standard. So, giving you a very high level view and giving you MAP-T in context, the various components. There's two functions introduced. They're really latch on. This is one of the things that I like about MAP-T because it doesn't create a whole lot of disturbance to most existing environments. We have two functions. We have the border relay. This is the provider side gateway function. As I mentioned before, it's mostly stateless, so it looks and feels like a router and less like a firewall in the case of some of the technologies that do stateful NAT. And we also have the subscriber gateway portion, which will either require a software upgrade or a different device. In both cases, again, it can be done via software on some platforms, maybe some hardware augmentation on others, or maybe an addition of a new hardware or software component if we're talking about something virtualized. So if we look at the subscriber addressing, if we look at the residential gateway, on the LAN side, it looks exactly like dual stack, right? We have the subscriber who assigns their own RFC 1918 addressing, or they could take the default, the manufacturer default, so that's the same. And then you have the provider assigned IPv6 prefix. On the provider-facing side, we no longer have an IPv4 address, as this mechanism uses a tunneling, stateless translation for tunneling purposes across the IPv6 domain. And we also have an addition of a notion of a MAP-CE IPv6 address. This is going to be the origination point for all IPv4 traffic that is tunneled across the IPv6 domain. One thing I want to note about this diagram is that though I show the BR connecting to the IPv6 internet, really in our implementation and most implementations, native IPv6 traffic is going to flow and avoid the BR altogether. You really don't want to push IPv6 traffic through the BR. I'm going to introduce you to some MAP-T terminology, though I don't want you to get too fixated on it because there are some visuals that I have in slides to come. There's a notion of a mapping rule. This basically associates an IPv4 prefix to an IPv6 prefix. The IPv4 prefix is, those of you who have done enterprise level NAT or carrier grade NAT, this is just a prefix that's used for the shared IPv4 address. This is what the subscriber shows up as on the internet when MAP-T is used. The IPv6 prefix is an aggregate of the prefixes assigned to individual subscribers. Now, the mapping rule is used by both the MAP-T CE and the MAP-T BR. On the CE, it is used to determine its posture. So it's given in the case of a shared IPv4 address, the prefix will actually communicate its IPv4 address. I'll show this in a little while. Its IPv4 address and optionally the layer 4 port allocation. In our case, it's mandatory because we're doing shared IPv4, but it also communicates the layer 4 port allocation. On the BR side, it allows the BR to perform the IPv4, IPv6 stateless translation. The base mapping rule is simply a mechanism to identify the actual mapping rule used by the subscriber gateway given a list of mapping rules. It's a longest match operation, and I'll speak about that a little bit later as well. Default mapping rule is very, very similar to the notion of a default route for MAP-T. It involves using and originating an RFC 6052 style prefix from the border relay. What you do with this prefix is you embed Internet IPv4 destinations within this prefix. Since this prefix is originated by the BR, any traffic that you're trying to tunnel through to the BR will be drawn by this route and processed by the border relay. It's very, as I mentioned, very similar to a IPv4 default route. Map domains is simply a mechanism to group a set of map TCEs with a set of map TBRs. We use it for scaling out the solution and distributing the load. And lastly is the notion of the embedded address bits. These are bits that are embedded within the user-assigned prefix. And this is going back to the ability of the subscriber gateway to be able to identify both the public address that they're going to use and the set of ports that they're going to use. That information is embedded in these bits. And combined with the mapping rule, it allows the CPE to determine its posture. So here's a little visual of what a MAP-T environment would look like. What I'm showing here is a implementation with 2 border relays, 2 MAP-T domains, each one of them having their own default mapping rule, and 2 mapping rules per domain. 2 BRs are implemented here for redundancy purposes. They have the exact same configuration. If you look at the way that we've color-coded this diagram, you can see how the individual CPEs relate to the domains, the default mapping rules, and the mapping rules themselves. It's going to be a little easier for you if you're interested to look at this offline, and you'll also be able to see the exact posture for each one of these CPEs, which includes the port sets that each of the subscriber gets and the public IP address. So the easiest way for me to introduce this topic to those of you who have not seen this before is actually taking you through a packet walk, a sequence. I actually do it in both directions to describe what's occurring. So first let's start out and look at a transaction from the subscriber to the internet. So in packet sequence number 1, we have a very typical internet transaction where the subscriber is coming out from a RFC 1918 address destined to a public IP address on the internet. This one happens to be TCP, destination port 80. That leaves the subscriber laptop, gets to the subscriber's gateway, and at the subscriber gateway, you perform NAP-T just like you always do, right? The only difference is that you have a limited set of ports to work on. You don't have the full 16-bit allocation like I mentioned before. So 4000 happens to be a port within the port set for this particular subscriber. So we replace the source port with 4000. We replace the source IP address with the public IP address that was signaled through the embedded address bits in the user prefix, and I will show that. So you replace that as well, and then obviously the destination stays the same. Now, sequence number 3, packet sequence number 3, still remains on that router, and this goes back to what I meant before, that the addressing is logically assigned. It never actually makes it outside the subscriber's router. So before it leaves the subscriber's router, we do the stateless translation. And here what we do is on the destination IPv6 address, we use the BR prefix as mentioned before, and we embed 1.1.1.1 in there. So if you look very carefully, you'll see 1.101.01 in the IPv6 destination address. Now the source address, what we do there, that's the MAP-T CE address, and embedded within that address is the public address 192.0.2.2. It's a little harder to see after the hex conversion, but it is indeed in there. C000, let's see if I can see here, 202 is the 32-bit representation of the source public IP address. Once the stateless translation occurs, since we did a pseudo header, we have a change in the pseudo header, we have to do a new TCP checksum because this is TCP. We place it on our IPv6 network. The BR prefix is going to draw that packet to it because that's going to be longest match. It gets to the BR. Now the BR has the mapping rules as well. It's going to do a longest match, and it's going to figure out where the bits are in order to extract the IP addresses. So in the same way that I was able to read this out, we know what the bit offset is for the 32 bits of the IP addresses in both the destination and the source. We pull those out, we switch the header out, we do the TCP checksum calculation again as the pseudo header is changed once again, and we put it out on the internet. Going back in the other direction is a little more complex, and in this particular slide I include some of the metadata that's included in the mapping rules and in the provisioning process. So we have our BR prefix, in this case it's 2001 DB8/64. The mapping rule is going to include one rule IPv6 prefix, 2001 DB8 101/48, and a rule IPv4 prefix of 192.0.2.0/24. As mentioned before, part of the metadata is the actual EA length in bits. In this case, it's 14. All of this is variable depending on how you decide to provision it, but in our case, it's 14 bits. Now, the source translation is easy. It's very similar to what we saw in the previous slide. We take 1.1.1.1 and we embed it in the BR prefix, right? The destination is a little more complex because what we're left with is 192.0.2.2 port 4000. How do you rewrite that so that you can get the MAPT CE address? So I have this slide to demonstrate that. So the first thing that you need to do is we look at that destination address and we do a longest match against all the mapping rules within the border relay. One of them is going to match on 192.0.2.2. You identify that mapping rule, and within that mapping rule is going to be the rule IPv6 prefix. In this particular case, it's going to be 2001 DB8 0101. So we take that prefix. Now this is again variable depending on how you provision and what your address assignment is going to be for the subscriber. You place that within the first 48 bits. And the next thing we do is we analyze and populate the bits, the EA bits. So the first thing, as I mentioned before, our EA bit allocation is 14 bits. We know that 8 bits of it is for the subscriber rule IPv4 prefix. Why do we know that? Well, in our particular case, the rule IPv4 prefix is a /24. /24, all the unique addresses in a /24 can be represented by 8 bits. In our case, it's 192.0.2.2, so it's index value 2 for that IP address. We populate those bits within the EA bits, and we move on to the port set identifier section of the EA bits. Now, the bit arithmetic for taking the port 4000 and matching it to the PSID is a bit beyond the scope of this presentation. I do have it, an example and a walkthrough in a document that I reference at the end of this presentation. So if you're interested in that, you can look there. But in this particular case, with this bit arithmetic, you take the port 4000, it'll match against a PSID value, an index value of 58. You place that in the PSID bit section of the EA bits. And now we're left with 2 bits plus the IPv6 interface identifier. This is a lab environment, so those of you who are horrified that I'm using a /62, let me assure you that's not going to be happening in production. But in this particular case, since we craft our MAPT CE out of the first /64 of the user prefix allocation, those 2 bits are zeroed out. We move over to the interface identifier as specified by RFC 7599. First 16 bits are zeroed out. The next 32 bits are the source public IPv4 address. And the last 16 bits are the PCID, once again, left padded. And the result is the packet you see there. Once again, we would apply the TCP checksum calculation as the pseudo header has been recalculated. And we ship it off to the CE. Now, the process on the MAP-T CE is the same as you saw previously by the BR when the traffic was coming in on the V6 side. It knows exactly where the bits are to extract the IPv4 address. And so that's an easy process, and the rest of it is normal NAP-T processing, stateful NAP-T. So what are the benefits? So as I mentioned before, the border relay is nearly stateless. And when I say nearly stateless, the exception is fragment forwarding. Why? Well, only the initial fragment is going to have the port information, and we need that port information to be able to craft the destination MAP-T CE address. So the subsequent fragments are not going to have that information. We need to keep state for this reason. We really like this technology because it aligns really cleanly with our existing IPv6 deployment. There's no additional logging overhead. We're already doing DHCP v6 lease notification, logging, and this is for regulatory reasons. And so combined with some of the algorithms, MAP-T is algorithmic based. It's very simple to match a particular internet transaction of IP address and port with a particular subscriber with beyond the DHCP lease notification, no additional logging. Extending DHCP v6 to support MAP-T is just a delta of an option 95. This next one was very important to us, which is supporting the existing 5-tuple use cases on our network, which includes classification, ECMP, and filtering. Integration is much easier than a number of the stateful technologies, specifically NAT 444. The forwarding, we don't need separate forwarding logic. If you want to support both legacy broadband, where you're doing dual stack or just native IPv4, and you want to be able to do MAP-T, you don't need additional routing instances, VPN, policy routing, any of that. Anything that is routing things non-natively, you have to signal, keep additional routes within BGP. This one is just native IPv6, IBGP in our case, and a native IPv4 IBGP. It looks exactly like what we're doing from a dual stack perspective. Something that we really like and we look to do in the future is IPv4 mapped IPv6 address. And this gives us the capability to take a resource such as CDN, place it within our network, address it with IPv6. So a client at the subscriber location that wants to access that resource natively, so if the CDN returns both a quad A and a single A record, if it's a dual stack client, it'll just access it natively over IPv6. But if it's an IPv4 only client, the translation will occur on the CPE. The client will access it natively via IPv4. The gateway at the subscriber location will do the stateless translation over IPv6, and the CDN resource will process it as if it was originated from an IPv6 client. Now, the benefit of that is, number one, we're going to once again avoid triangular routing, right? The traffic does not have to go through the BR. But another great benefit is that we eliminate the load for this high bandwidth application from the BR. So that is a tremendous benefit. So if we look at this technology compared to some of the other transition technologies, we have the notion of subscriber assigned address scalability. With NAT 444, that can be a problem. We have RFC 6598 addressing, that's a /10. It's typically used in a NAT 444 environment. For smaller service providers, that's okay, right? A /10, that's a lot of address space. But for a large service provider such as Charter, where you really want uniqueness, that's problematic. And it drives us to do things like overlap or potentially use address space that we really shouldn't be using. I won't say the word squat. In the IPv6 cases, obviously, we have IPv6 address scalability, which is more than enough address space to uniquely assign to each one of the customer gateways. Asymmetrical forwarding, since it's a stateless technology, MAP-T supports this, as well as MAP-E and lightweight 4/6. The stateful technologies, DS-Lite and NAT444 do not. 5-tuple visibility, as discussed in the, previously, MAP-T supports it, NAT444 supports it, since we're talking about only double translation, but those that do encapsulation, you're not going to have 5-tuple visibility. Software requirements for the CPE. Most of the technologies that are IPv6 based are going to require new software, some sort of augmentation on the CPE. But it can be argued that NAT444, to fully implement NAT444, where you implement PCP, that would require new software as well. Most residential gateways do not support PCP today. Address allocation and NAT efficiency. This is one of the weaknesses of MAP. MAP pre-allocates its address space, its NAT address space. It's not as flexible in terms of where you utilize your public address space and how you can distribute that address space across your footprint. It's sort of fixed. So the stateful technologies have an advantage there. Lightweight 4/6 has additional flexibility from that perspective, but it does come at a cost, which I'll discuss in a moment. Support for IPv6, client access of IPv6 resources without a gateway. This is what the example I gave before with the CDN. That's something that's exclusive to MAP-T, given the technologies that are listed over there. Encapsulation overhead, anytime you do tunneling, you're going to have encapsulation overhead. MAP-T is more efficient than the other IPv6 based technologies, as it does header translation as opposed to encapsulation. To tell you the truth, I don't see that as a huge thing. NAT444 avoids it completely, again, because it's doing double translation. And lastly is the signaling integration between different components on the service provider side, as well as signaling integration between service provider components and subscriber components. MAP-T and MAP-E don't require it, don't need it. NAT444 and DS-Lite can need it between the large-scale NAT function and the subscriber gateway if you want to do PCP. And in the case of lightweight 4/6, you need it to support, you need signaling between the border relay and your provisioning system. That's how you get your flexibility with the NAT efficiency. MAP-T at charter communication. This is the work that we've done so far and where we're at. We have implementation from 5 commercial vendors, a number of them people would recognize in this room. We have hardware acceleration from 3, and we are able to get gig rate throughput with those. They also support base mapping rule from 16 mapping rules. This was important as it gave us some efficiencies so that we don't over-allocate IPv4 address space before we have enough routers in the field to support it. So it allows us to incrementally roll this technology out without over-allocation of public IPv4 address space. We have 3 commercial implementations for the BR. We're currently seeing roughly 150 gigabits per second per 1U. It's easy to distribute things out. That's why I characterize it as 1U, and we anticipate improvements given new hardware and software optimizations. On the provisioning side, as I mentioned before, this was simple. Day 1, it was easy to extend IC DHCP to support MAP-T provisioning, and it didn't take us very long to work with our commercial vendor to not only support option 95, but to also support the multiple mapping rules. I'm proud to report that we're currently undergoing early field trials, and that we hope to share some of the data when we we have it available and ready for public consumption. I have one last slide here. It's just some references that you may be interested in. There's obviously the RFC. There's a Cable Labs map technical report, which includes a walkthrough through the algorithm that allows you to identify the port set ID from the port, and also a Python package that I created. We've used it to do a lot of the map calculations in the lab for test traffic generation and also validation of implementations. And it's also the basis for our regulatory web service that resolves a public IP address and port to a particular subscriber. Again, that's important for regulatory reasons. And I'm done.